All right, let's set the scene. So we're trying to predict stuff. We've got data. We know how to test hypotheses about existing data, but now we're like, what if I had a new data point that I haven't seen before? How can I use what I've got to make a prediction? So we learned one cool way, and that was involving this nice measure of linear association, R, our correlation coefficient. Say that 30 times fast. All right, so that R value tells us how closely packed these values are on either an increasing line if R is like close to 1 or a decreasing line if R is close to -1. And there's everything in between. You just don't, it's not linear at all if it's close to 0 though. That's the problem. So yeah, if it is slightly linear, you can use that for prediction purposes. And so you got a lot of points. We can figure out where the best line is through those points. R kind of gives us that in a certain sense when the values are in standard units, but we can convert it back, and we learned these beautiful formulas last time that are important to know, but you can just write the functions that do it for you. But this is how you solve for, all right, somebody gives you a new x value that you've never seen before. You would like to predict like a new height of the parents or something on average. You'd like to predict an estimate of how tall the baby's going to be. That's what we want. And so given all these things, we can find the slope of that line, that regression line, and also the intercept of that line. And we got some formulas for that. Slope is that in the original units, or intercept is that in the original units. And the last thing we talked about was, okay, we've made these estimates. We've drawn a line, the best line that we can in theory, for some definition of best. I'll show that to you. And we want to know how well was it how good of a job did it do predicting things. So let us rewind to last time we did this. So we got our baby table. Boop. So here it is, where you've got maternal height, and we selected height of the mother and also the weight of the mother during pregnancy. That's decently correlated if you think about it, right? A taller mother is going to weigh more during pregnancy. That seems like there's a line going on there. The correlation is not perfectly 1, but it's 0.43. It is positively correlated decently, but there's a lot of like options, right? For the best line that goes through it, this is our regression line. Like if the mother is 60 inches tall, we've got a bunch of data points showing a bunch of different mothers who are 60 inches tall and how much they weigh. Not everybody weighs the same if you're 60 inches tall. And so this midpoint, which was like 115 or something pounds, was our best prediction of the mother's weight if they were 60 inches tall during pregnancy. But you see that we have a bunch of different points along this line that are not at all 150. Okay, so a bunch of different mothers in our data set. This line is predicting like the best options that we could possibly have, but it's not going to predict everybody always perfectly. So we would like to know, how far off are we? And so we can calculate the slopes, the intercepts, and we did all this. Let me re-include all these formulas. I need these functions, right? Correlation, slope, intercept. Just solving all those things. So bring them back. I can rerun all this. Hopefully it still works. Got a fit line. Correlation. See, I needed standard units. Well, let's go define that. Where was that? Standard units. There it was. So that exists now. Dun, dun, dun. Can I rerun it now? Got a lot of things in this file. Hey, okay, we've got everything right. So okay, it looks like, yeah, when we're estimating weight given height, the slope of the line is 3.57-ish, and the y-intercept was -100-ish. And so using that, we're able to make predictions. So like given every mother's height, we can predict what the line was going to do. Like we can draw this line ourselves manually now. The way you do that is you take the entire column that was your x values, take the maternal height values, and then run it through our predictor, which has a slope. So these are the x values. Here's m times x plus b plus the intercept. See that? So it's doing the prediction and it's attaching this linear prediction value to this as a new column. of this brand new table, and we can scatter it and we can see the line. So for every different value, we have one prediction. That's the one that the line gave us. And so you can see that table here. All right. So does it kind of make sense how we made this table? We used our regression estimate to make a prediction given the slope and the y-intercept of our best fit line. And so we're trying to use height to predict weight. Here are our predictions. And here were the original values of the actual mothers in our data set. So sometimes it's not that far off. Sometimes it is. It's going to be in between for a lot of people. Okay. So yeah, that's the idea. And that's where we stopped. Does that make enough sense? Okay. So now the question is, how far off were we? We can calculate what's called an error. So the error is the actual value that was in our data set minus the estimate that our predictor is telling us. So it doesn't have to be just for regression. There's a special word that means a regression error that we'll get to later, but this is just called error. It works for any kind of estimator. Yeah, some of the errors are positive, some of them are negative, bless you, because we're not taking absolute value or anything. So, for example, this first one, our actual value was 100, and this was our other value. Ooh, I almost had a sneeze too. Never mind. Okay. So yeah, actual value minus the estimate. So if this is our actual value, this is our estimate. You see that we're gonna have a negative error here. So we predicted too high. We should have predicted less for that one. That's kind of how that's saying. So yeah, some of the errors are positive, some of them are negative, and so let's write that down. Let's add that as a new thing in our table. Let's see here. I will take baby with predictions and add a new column. This is our new stuff after the line today. Baby with predictions. And yeah, let's just keep track of all the errors first. So how do we get all the errors? That's it's always actual minus estimate. So it's this column, actual, minus the linear prediction column. So maternal pregnancy weight column minus linear prediction column. So that is baby dot column, that one. Minus baby.column, this one. Prediction comes second. That's just how they've defined it. So there's my errors, and I can attach that to our table. I can say baby with predictions. Hey there. Baby with predictions, and then with a column called error. And then I can place our errors there. And there's that table. Let's see here. Not in the table. Oh, did I do something weird? Oh, okay, yeah, I have to create all these again still, sorry. Do. Are we happy now? Linear prediction is not in the table. I must have spelled it wrong. Oh, it's not baby, it's baby with predictions, sorry. Give me those. There we go. All right, so that's essentially, I took this and I subtracted this from it. So there are all my errors, how far off I was. I was off in the negative direction there. I was off in the positive direction here. Should have been bigger, right? Should have been smaller, so it's a negative error. You see that? So those are my error values, and I kind of want to just see, on average, what was the error, right? Some of them are positive, some of them are negative. We would like the total amount of error. So I hope you see that you don't want the positives to cancel out the negatives here. Does that make sense? I want how much error was there at all ever. We don't want a positive 10 error canceling out a negative 10 error. That should be 20 error total, right? Does that make sense? I want to remember how much real error there was. We don't want them to cancel out. I wonder actually what would happen if we if we did this, the average. Should I call this something? What's the average error? NP.mean errors. It's 0. You see that? And which should make sense to us. It's how far away things were. It's canceling things out. So this is a useless value to us. It's so close to 0. We know that the error is decently large for a lot of things. Yes. So we would like to get rid of any negatives so that this does not approach 0, just due to the nature of the math that's going on here. All right. So we could either take the absolute value of every error to know just how far away was it always, and add those up, take the average of that, or we could do something else in math that would cause the negatives to go away. We could square them. That's another thing that people do. That's somewhat better for mathematical purposes. It's a better function. So we're going to square this time. So we're going to square the errors. That gets rid of the negatives. But then we've got, if we take the average now, it's a little weird. The units are now squared units. So what everybody's decided is, we've all decided on root mean square error. That's the idea. So what we want to do is we want to take our find the errors, square them, get rid of the negatives, take the average, and the units are now in squared units. So take the square root of that average to get back to the original units, and that will tell you kind of like, on average, how far away was everything. How far off were all the predictions, okay? That's called the root mean square error. So it's definitely a mouthful, but yeah, that's how you do it. So before you take the root, it's called the mean square error. So the MSE, mean square error, is, all right, give me all the errors, square them, star 2, take the average of those, np.average or np.mean. That's the mean squared error. 348 units squared, I don't know, pounds squared, I guess. And then the root mean squared error is RMSE for short. That's just you take the square root of all that. So it's, I guess, from scratch, take the mean squared error, and then to the 0.5, take the square root right afterwards. See that? So it's about, on average, we're about 18.7 pounds off each time we make a prediction. Does that make sense? That's a good number that tells us, like, how, on average, how far away are we when we're doing these predictions using linear regression. All right? So that is a beautiful number, and that's how you calculate it. And what I'd like to do is give you all of this code that I've written so far. You've got all the ones from last time, but the stuff that I just wrote today is important to have. So let me give that to you, because I want you to try some stuff. Boop. So if you go to our code from class, just like the last lecture or something, you can find our chapter 15 stuff. You know where all the data sets are as well. But what I'd like us to do now is try some stuff, try some things. So just like we were trying these data sets before when we were calculating R, let's go back to them. So let's get the sun's heights data set. Let's import that table, sun's heights.csv. And we know that father and son were the best ones that predicted each other. So father's height's predicting the son's height. Let's draw the regression line and calculate the root mean square error of those predictions. All right, that's our question. So let me get that started for us. But I want you to try that. Crushed, nice examples. So we'd like to include that new table, sun's heights. And we'll just select out the father and the son in that order. That's all we care about right now. So there is that table. And what we'd like to do is use father to predict son with linear regression, figure out what is the predicted value for each of the father's heights, like how far away is it from the actual son's heights. And so try to draw the regression line by yourself manually, and then calculate the root mean squared error. So what you'll want to do is scroll on up and do pretty much everything we just did right here in error and estimation. Does that make sense? So you'll follow through with the same idea. It's like, instead of maternal height, it's father's height. Instead of maternal pregnancy weight, that's the predicted thing, we're doing son's height. Okay? So do this is like the automatic scatter plot. Instead of that, I mean, you can do that first if you like, but just try to do all the same stuff, find the correlation value, get the slope and the intercept for father's height predicting son's height, and then this is the manually made regression. Does that make sense? The scatter plot. You get to see our linear prediction next to the actual values as little dots, and then you can attach it to a table, and you could start finding the error values like that. And what I would like is the root mean squared error. So you got the slides, you got all this. Here, I'll show you the root mean squared error calculation at least. That's how you do it. So yeah, essentially, instead of maternal height predicting maternal pregnancy weight for this data set, you're going to follow all these things all over again and try to use father's height to predict son's height. Does that make sense? Questions about that? So there's a lot involved, but you can just walk through what we were doing last time if you go look at our code and give it a try yourself. So I'll be here to help. I want to give you a few minutes to play around with that so that you get comfortable with these ideas. Yeah, I don't want to do that. Just want to do that. There we go. So I think this one was decently correlated. It was more than like the 0.4 that we saw for the maternal pregnancy height to maternal pregnancy weight. So we might get empirically smaller yet. What we did on a root mean square here. Maybe a few minutes head start. What should we do? Let's see what to replace with what. Let's see. All right, I'm gonna stop the timer before it yells at me. So let's try this together. Let's see what we got. Did any questions come up as we were trying it? You kind of see the pattern there. Let's do it together. We've got, all right, if we want to calculate predictions, I don't have to even draw a graph yet if I don't want to. I can say, all right, I'm going to calculate the best fit line given regression, given linear regression, and that involves calculating the slope, right? I got these functions. I've got the slope function, all these guys. The slope function, the intercept function, that will tell me the line itself, given my table and the x and the y label values. So like heights mid-parent child, that will give me the slope of the intercept for the data set I care about. And so I want sun's heights there. So m is my slope, right? Give me the slope for the sun's heights table, where it's father on the x and sun on the y. Father predicting sun. And then b is your y-intercept, right? mx plus b. So that's intercept now. Just let the function do it for us. Do the hard work to find the y-intercept for that best fit line. And then we can do that. We can use now these values to create predictions. So the predictions that we can have are, it's always based on the father column, right? So go get that father column. Sun's heights dot column. Oops. Father. So get all those x values and like multiply them. It's mx plus b. So m times all the x values plus b. Now we got a bunch of predictions for sun. Does that make sense? That's how it's going to work. So, all right. And then we know what our table looks like right now, but we can attach that column. Sun's heights dot with a new column. Those are our predictions. Predicted sun height, let's say. And those are our predictions. Something like that. So there we are. They're decently close this time. That's a little bit better because the correlation, I think, was a higher number. R value was a bit higher. So that's not horrible, at least for the starting ones. Let's see if that's happening everywhere. Maybe I can call this, I don't know. I'll just call it sun's heights again. Put it back into the table itself. Cool. And so now I can do a scatter plot on sun's heights. Dot scatter with father on the x and then everybody else on the y. And there is our manually created regression line. So yeah, that's the value. It's obviously not perfect still, so we now want to calculate the error. How far off is it on average? Root mean squared error. Are we ready for that? Does this part make sense? All right, so the root mean squared error is you got your it's going to be actual minus predicted. Oops. Actual minus our estimate. So take this sun column, subtract predicted sun height column. That's what we want here. So those are our errors. It equals sun's heights. Give me this value. So it's always actual minus estimate. So give me the actual sun column, subtract our estimated sun height, which we called predicted sun height here. So those are my errors, and I can attach that. Sun's heights with a new column, all error. Well, put all the errors on there. Okay. So there they are. They're decently small. They're a bit smaller than the last one. So we can calculate the root mean squared error by taking all of our errors, squaring them first, taking the mean after that, and taking the square root to go back to the original units. Yeah. So right before you take the square root, that's called the mean squared error. So like do the squaring of the errors. error squared, take the average, NP dot or mean, and then the root mean squared error is take the square root of all that. And it looks like the root mean squared error of our predictor is, given our linear regression estimates, it's about 2.2, I guess it's inches. And that's much better than the other one. That's quite nice. So that's a decent, a better predictor, I guess. Father's height was better at predicting the height of his son. Nice. And so, yeah, that's that example. Are there any questions about it? See how it's working? All right. Yeah, I just want you to try a couple more of those. Do the same thing for cereal and the same thing for Pokemon. If you want to do both at the same time, go for it. But I want you to try it. So we did some stuff with a cereal table. Go and include that table. Pick some numerical variables, some ones that you care about, and draw some regression lines. Do them automatically this time. You can say fit line equals true. Remember that? Go look at our examples, and then calculate the root mean squared error of your prediction for, I don't know, fiber versus potassium or something. I don't know. Pick your favorites. Pick the ones with a good correlation value. Yeah, give that a try for both cereal and Pokemon if you would like. And then I can do both as well. It's like pick two of your favorite numerical variables and get some practice calculating the root mean squared error and drawing the regression lines. It's okay if it's automatic now. Now you know what it's like. You still have to call slope and intercept to get the values to do the error calculation, though, for sure. You want to do it for Pokemon and Cereal? Go for it. I'll give you a decent head start on this. Scroll back up. Sorry. In the code from class last time, we did some correlation R value calculations to both of those data sets. Find some good ones. Fine. Let's use those. Let me know if you have any questions. What were the good ones for cereal? Fiber and potassium, yeah. Surprise, I don't understand that. Does anybody have a good idea as to why that's true? Because I sure don't. It is just found in fiber. Hmm. Another minute or so to try stuff. Oops. All right, that's my timer. I did a Google search, and I don't know if we trust the AI answer that's at the top, but it said that just like they go hand in hand because a lot of high potassium foods are also naturally rich in fiber. Interesting. And also apparently more fiber can affect how your body absorbs potassium. So maybe just the fact that there's more fiber there means it's happier and it can take more in even if there's the same amount. So that's confusing to me, but now we know. So yeah, any questions come up as we tried this stuff? Get a feel for how this all needs to come together. So yeah, let me try it. We'll do fiber and potassium for sure. So let's get our cereal table going. Let me scroll down in my notes. So I need the cereal table. Let's just get them both at the same time. I got cereal, I got Pokemon. So we got our tables. The cereal table is interesting. And it looks like, yes, we know that the correlation of, what was it? Fiber and potassium. What are the numbers that are a bit different? It looks like potassium ranges a lot. Sometimes it's -1. I don't like that, but we'll figure that out together. And then fiber is some smaller numbers here. Interesting. So yeah, I think that's all right. What else do I want to do? No, let's just look at the correlation. We can figure out which is on X, which is on Y in a second. I guess it doesn't really matter. Oh, sorry. Correlation, we need the table itself. Boop. So 0.90, that's beautiful. So I guess the question is, should we have fiber predict potassium or should we have potassium predict fiber? What are our thoughts? Could go either way. Do we have any serial dot scatter? Well, let's take a look at one of them. Let's do it in the order that I just typed it. Do fiber, then potassium. Fiber on the X. What does it look like the other way? Does it look more like a line? It shouldn't. It should be pretty much the same thing but flipped. But I don't know. I guess the different values of potassium, there's more different values. There's more different X's than that we could use. That's my thought, maybe. So maybe let's have potassium be on the X-axis. That would be fun. So, all right, if we want to predict like that, potassium first, potassium predicting fiber, then, all right, we're going to do some function calls, right? We got to get our slope. The slope of our best fit line for the serial table where potassium is predicting fiber, and same for the intercept, right? Let's try to do it all together. So B is that. Intercept. And we can get our predictions based on that. It's just like go to the serial table, take out the column that is our X values, so the potassium values. Potassium values. That's our X's. Do MX plus B on those. There are our predictions. The errors, right, are going to be, I guess, sorry, we can do the fit line equals true as well. Ta-da. So there's the fit line. We've just calculated the slope and the intercept. The error values are just like take the column, take the y column, the values that we're predicting, the fiber column, and subtract the predicted values for fiber. And that's what we're getting from our best fit line. So those are our errors. You can look at them if you want to. Here they are. They're decently small because it's a highly correlated thing. And we can do the root mean squared errored. Right? So how do we do that? So we're gonna square the errors, take the mean, so it's root mean squared. You do it, you think of it like backwards, right? Root mean square. So square, then mean, then root. Just like something we've seen before, right? Square, then mean, then root. And that is our root mean squared error. Boop. And it looks like it's 1.02. It's off by that many grams, I guess. So I think it's fibers in grams, I assume. Or milligrams, I'm not sure. But something like that, and that's the way we calculate it. Any questions about that? Yeah. And you better believe we can do the same thing for Pokemon. We can pick a couple things. What were the highest? We tried them all, didn't we? We caught them all. What were our highest correlated values here? Looks like it was defense and special defense. I don't know. I like attack and defense. Why don't we use those? That'll be fun. So just the same stuff. Exact same stuff. I could copy and paste all of this, essentially. We can do attack and defense. Let's do a scatter plot first. So Pokemon.scatter. We got attack. Let's have attack values predicting defense values. Fit line equals true. Boop. So they're kind of all over the place, but they are positively correlated. You can look at the correlation value. It was like 0.45. And yeah, if we have that, it's going to be the Pokemon table. Pokemon. And it's going to be these two variables. Attack predicting defense, attack on the X. And so to create the predictions, we're going to use MX plus B. To do the errors, we're going to use the Y values, the existing Y values, subtract our predicted Y values. I think I changed them all over. That looks right to me. And so it looks like the root mean squared error now it's a little bit more because it was a bigger range of values and the correlation wasn't as big, but it's 27, I don't know, defense points, whatever that means, whatever that unit is in Pokemon Land. I have not played it in long enough to remember. But yeah, that's another way to calculate that error. That's telling us in just one number, on average, how far off are our predictions given this estimator that is our linear regression estimator. It could have been something else. It could have been our other kinds of predictors. Remember that we also had the nearest neighbor predictions, where we took just like, give me all these guys, take the error average, things close by. That's another way of predicting stuff. We'll look into that more in a couple chapters. But linear regression is easy because it's like you got one value predicting everybody. Just like read it off the line. Okay? So I think those are some good examples. Are there any questions about those before we move on? Not horrible, right? So yeah, let me show you some cool stuff. There's a function in our library, in our data science library, called minimize, and it takes a function and it gives you the inputs that produce the minimum value for that function. It's really cool. It's really fancy and fun. It's called minimize. Boop. So minimize, it legitimately takes the name of a function that you've made. It's like, here's a function that you've made. you call minimize on it where it takes like floats as inputs, and it gives you the values that give you back the smallest answer for that function, which is really cool. All right. So I want to prove to you, like using this, that this linear regression line really is the best line. It's the one that we want to be studying. All right. I haven't shown that to you. So I think if you want to predict a good line that goes through your data, right, the goal would be to minimize some type of error for that line, right? So we would like to, let's say we want to minimize root mean square error for a line. That seems logical, right? Because our regression estimate was a certain slope and a certain intercept. There could have been some other slope and some other intercept that was a better line through the data that limited that root mean squared error more, right? Let's see if that's true. The hint is that that won't be true. So let's show that minimizing the root mean square error of some line, a function that tries to find the root mean square of a linear estimate, and we'll watch it be the same as the regression line. So that'll be fun. So let me just show you minimize in the first place. It's really cool. So it's a very nice function. So we'd like to find a function that minimizes root mean square error. Boop. If I could spell. So let's make just a simple function, like a parabola real quick. MP, some x values are 1 to 3 by 0.1s. Some y values are all the x values, I don't know, -2 squared plus 3. And here, let's make a table with the x and y values. Table with columns. The x values are x's, the y values are the y's, and I would like to plot as a line plot using x as the x-axis. So I just made a bunch of x values and y values that are just like dots, essentially. I've drawn lines between them, but I've drawn a parabola. Yes. So these define a function, right? This is like y equals x minus 2 squared plus 3. That's the function itself. And we see that its minimum is right here, right? Its minimum is x equals 2. Yeah. The minimum value is achieved right there. That's the bottom part of the parabola. So we can turn this into a function, like this y equals that. Let's turn that into a function. So it's like define a function called f, takes an x. It returns back the x value minus 2 squared plus 3. Exactly the same. Exactly the same thing as what we were doing. And we can ask the minimize function to minimize f. You say the name of the function and watch that it finds 2. It finds a value close to 2, essentially. Super, with a few decimal places of precision. So it's found that, yeah, 2 is the number that minimizes the value that results, that f gives back. Isn't that cool? That's a lovely function that does that for you. It's very powerful. You know that there's some fancy calculus involved if you've taken a calculus class to find that. Let's make a function that gives back root mean square error for a particular slope and intercept, because that defines a line, yeah? And let's go back to this example of the baby maternal height, maternal pregnancy weight stuff, okay? So all of this was what we had from before, a regression slope, a regression intercept. It was these guys. Oop. Let's remember all that. And let me prove to you that this worked out well. So this was for our baby stuff. Slope of our regression line for maternal height predicting maternal pregnancy weight, slope and intercept. Here they were, okay? And let's make a function. It's going to be an interesting function that gives back the root mean squared error for any line. So you give me some slope of a line, you give me some intercept of a line, whatever you want to give me, and I will calculate the root mean square error of trying to predict maternal pregnancy weight from maternal height, given that line. Does that make sense? So you give me a line that doesn't have to be this one. Maybe you have a better one, a better M and a better B, right? And then we'll figure it out. So, okay. If we got our x values, right? Our x values are the baby table with the column called maternal height. We're using those to predict maternal pregnancy weight. Yeah, so there's x's, here's y's. That's the same thing, but this column. There's our y's, and our estimate, given the line that you want to try, is slope x plus intercept. Does that make sense? You give me a line you want to try, and I'll give you the predictions. So give me that slope times our x values plus the intercept. You call me with that, and I'll give you some answer. Those are the estimated values. And we can give back the errors by doing the root mean squared, right? Root mean squared error. So the error itself is the original y's minus the estimate. The squared errors is us squaring that. The mean squared errors is we take the average. And the root mean squared error is we take that to the 0.5. That's the root mean squared. Did you kind of understand what this function is doing? It's like you give me some line that you think is a good one, and I'll calculate the root mean square error of using that line to predict y values from these x values. Here are my original y's. I can calculate the error of your estimate. Does that make sense? It's a little weird. But that's a function. You could call it with these values. This was our regression prediction, right? That's what regression said was like the best line, the best slope, the best intercept. But maybe there was a better one. Minimize would find it. Let's see. Because you could say like RMSE with, I don't know, 5 and negative 100, negative 110 or something. I don't know. That would calculate a root mean square error of 83. All right, that's a thing. You can give it different values. Like, all right, pretend that it's the slope is 50 and the intercept is 100. That's a horrible estimate. The root mean squared error is disgusting. That's not a good line to use to predict y values from our x values. Let's minimize it, though. Minimize RMSE. And I have to say smooth equals true to get it to do it right. But this is the best slope and the best intercept that minimizes the root mean square error of a linear estimator. Because we're using some slope and some intercept. Here's the best slope and the best intercept that minimizes the root mean squared error because that's what this function gives back. And what do you know? These values are exactly the same as our regressions estimate. That's all I'm trying to say right now. Linear regression does give you back the values, the slope and the intercept that minimize root mean squared error. That means it was the best line for that definition of error. Does that kind of make sense? That's proven it. That's proven it to us. That's wonderful. So, moral of the story, the regression line is the line that minimizes root mean square error. That is lovely and wonderful. Okay? So yeah. Any questions about that? That's a fun one. I like that a lot. Let's see, what else did I want to say? So, not too many slides left, but a few things to say still. This minimize function is great, even for and root mean square error is still great as well, for non-linear data. Because we know that there's some data that don't look like a line. They don't follow a line as a pattern. So least squares minimization is useful for non-linear data too. Let me show that to you. There's a cool data set for it's like Olympians or just like somebody on a high school track team, I guess. But there's a table called, or there's a data set from the book called shot put. The people doing shot put and how far they could throw the little ball thing. So like here is the weight that a person could lift, like their maximum thing that they could do 5 reps on or something. And then here's the distance that they could throw the shot put ball or whatever it's called. And if we scatter plot that, we'll notice that it's a non-linear trend. So let's do a scatter plot. Weight lifted. So do you kind of see how it goes like, it's more of like a curve, the trend there. You could think that there's a line there, like even the correlation's still not horrible, honestly, but I think it's better to do a line that is not a line. All right, so let me show that to you. So we can find like the best fit line. We can also find the best fit quadratic function. I hope that makes sense. We could play the same game that we played right here. Give me a function that gives me back the root mean squared error of whatever predictor you're trying to predict. So we can do the same thing for a line. Let's do a line first. So let's see, how do I want to do this? Yeah, I think here, I'd rather just copy and paste it because it's going to be the same stuff, but slightly different. And I want to finish these slides today. Whee! So here's what I want to do. Boop. Here is a function that works for, you give me any slope, you give me any intercept again, just like let's pretend it's the best thing is a line right now. Here it is, and let's try to minimize this function that gives back the error of using this line to predict shot put distance given the weight that you've lifted. So that's our best line. Boop. It looks like this. So that's the x value and the y value, and we can graph that. Let me show that to you. Whee! Copy paste, just very quickly. So we take, this is the m, right? The slope is the first thing, and the intercept is the second thing. So that's what you see here. It's just a little disgusting code that does that. But here's the line, the best line that predicts it. So we could have done the same with regression. This is the regression estimate because we're trying to minimize the root mean square error of a line with a certain slope and a certain intercept. So this is the best line that goes through the data, but do you see how it's like not really using this one very much? And like it should be more of a curve. That would be a little bit better. Yeah. So that's the best one there. And let's see here. How do I want to say this? Yeah, I think this makes sense, but like it's not really taking into account this dot, which let's pretend is not an outlier. I think a better trend is a curve that looks more like that. Yeah. So with that in mind, let's make a function that minimizes not a, you give me a line equation, but you give me the equation of some arbitrary quadratic formula, right? So not quadratic formula, but some quadratic function, like some y equals ax squared plus bx plus c. Like that's an equation of a quadratic function, right? Does that make sense? You give me some a, some b, some c, whereas a line would have been mx plus b, right? You give me two values, and that's how I can compute a line. You give me three values, and I can use that to compute a some weird-looking parabola thing, yeah? So let's make a function that takes three things, your best guesses for the a, the b, the c values, and let's see how far that how far off that is, and like what's the one that minimizes a root mean square error for a function that looks more like that, because that's a thing. So let me, I think it would be best for me to change this and type this one out for sure. So instead of you give me some slope and some intercept, let's do not linear RMSE, linear root mean square error, but let's do quadratic root mean square error. So still, you're using these x values to predict these y values, but it's, you give me an a value, a b value, and a c value that mean these things. Give me an a, b, and a c, and I will use that quadratic function that these define to see to produce an estimate, right? So my estimate now is ax squared plus bx plus c. Does that make sense? So take the x values, use a, b, and c like this to predict y values. Those are my estimates. Everything else is the same. Like the root mean square error is still the same. Here's the y values that they really were. And our estimate for a given a, b, and c of a given quadratic function, the error is that still. The squared error is that. The mean squared error is that. The root mean squared error is this whole final thing. Yeah. And so if we minimize that, minimize the quadratic RMSE, what do we get? I'll call this best quadratic function. It looks like these values, like they're pretty small for these ones. This one's a normal looking value, but that gives me a different kind of function. So that's a value for A, that's a value for B, that's a value for C that minimizes root mean square error. And let's draw that in the same kind of way. Boop. So here I am cheating and taking some code because it's doing the same stuff. It's like, all right, this first thing, item 0 was the A value, item 1 was the B value, item 2 was the C value. So here I am producing the values right there for all the weights. And I can make a scatter plot of that. And so here is the best quadratic curve. Do you see how it's nice and curving between things? That was the best one that the function found, the minimized function found. It goes between all the points. So you can use that idea to not just estimate a line, but to estimate any kind of function. Any kind of function that's not horrible. All right. So let's see what the errors were now. What was the shot put linear RMSE for the good values that the linear one gave us back? It was these. This was our best linear values for the slope and for the intercept. Like that was the RMSE for the best line. And let's do the same thing. We had a function that did quadratic root mean square error. And the one that minimizes the values there were these inputs. This A, this B, this C. We got a smaller error. That kind of goes to show that it really was probably a quadratic function that was underlying all this idea. So like the more weight you lift, there's like a cap, I guess. The more weight you lift doesn't mean you can, like, if you lift another 20 pounds, it doesn't mean you could throw another few feet as easily. There's like a cutoff. It gets harder and harder, apparently. So that's interesting to think about. I don't know. Maybe that's what that says. But you can use this minimize function to predict any kind of estimate. It doesn't have to be a line. That's all I'm trying to say. All right. But root mean square error is a great way of finding the best one. You give me, I want to minimize the root mean square error. That's a good number that like tells you how bad your estimate was. Okay. That's what I wanted to say there. So you give any kind of function that works like this, you can minimize it. It's nice. Any questions about that? That I did copy and paste a lot of code, but it's more of the idea that I want you to understand for this little subsection.
What would you use to minimize for besides error?
That's a great question. In this class, it's probably more like error. What else? I'm trying to think of an example that doesn't involve calculus. Yeah. Let's see. Yeah, it's just like you've got a data set and it corresponds somehow to like some sort of hyperdimensional surface and you want to find the smallest value there. This will help you find that. I don't know. I have to think. But for us, error is a great one. What else could we want to minimize here? Yeah, I'd have to think about that. I'll get back to you. That's a great question. Other questions? Let's see here. Yeah, so that's minimize in general. And now let's talk a little bit about the graphs of those errors. When you do linear regression, there's a different term that we use for the errors. It's called a residual. So we said error means any kind of estimator, but a residual means it was your regression estimates error. So a residual is your observed y minus your regression estimate for y. It's the same formula as the error. So it's just the distance between your point and the best fit line, which we know now is the regression line. And so if you plot your errors, or your residuals now, that's the new name for it, you should see some things. So a residual plot, in theory, it should, if you have a linear relation, a true linear relation, a linearly correlated thing, your plot of your residual values or your error values should be just amorphous. It should not look and have any kind of pattern at all. But if you see a pattern, that probably is indicating that your data really wasn't linear. There was something that was off. So there's a cute little example that involved the, what is it? This animal called a dugong. And like how wide they get with age. That's apparently not a linear thing. There's like a cutoff. So we'll watch you see that. We'll we'll discover that together. I will show it to you. So let's see. Yeah. Dun, dun, dun. Let me show all that to you. This is residuals. Boop. So let's see. I do want to copy and paste some more things in just really quick. This is useful. Here are all the functions we've ever used so far in this lecture, in this set of slides. So this is just with doc strings and everything taken from the book. So we can convert things to standard units, we can find the correlation of things, we can get the slope of the best fit line, which we know is the best fit line with respect to the root mean squared error. We can get the intercept, and here's a helper function, one more, that just gives you back all the estimates very quickly. It's like, all right, here is the slope, here is the intercept, take the x values, multiply them by this is like m, this is like b, right? Maybe I should call that m. Slope is m, there, mx plus b. Ta-da. So that predicts things. So that's all the values. Those have been fitted to our estimator. They're fit on the line now. So yeah, let's go back to, do I still have a heights table? No, I don't. Where did I include that? There it is. So it's family heights, all these things. Here, let me recreate these. Oop, there's my heights table. All the way back down here. There we go. So here are my heights. We got mid-parent, and we're going to try to use that to predict the child height. All right. That's what we're going to do. And we know that we could make a linear estimate with our regression and find like the best values, and those are called the fitted values. Now you can say that. All right. So heights. Let's attach to the end of that heights with a column. All our fitted values are our estimate values for the heights table, where we're using mid-parent to predict child height. Ta-da! And so that's just our estimates. I'll make that back into heights. There we go. So here, mid-parent, the child, and here's the fitted value, which is just another name for our estimate. Our estimate using linear regression of the child height. And you see that it's off a little bit. Okay? So we can make a function that calculates the residuals as well. Because what is a residual but an error? It's just like take our observed y values, subtract our regression estimates for y. So take your y values and subtract the fitted values. That's how you can define that. Oops. Give me our residuals. So for a table, for an x column and a y column label, our actual predictions are the fitted values. That's another name for it. Got a function for that now. And then what we want to give back is the y column of that table. That's the actual y values minus our predicted y values. That's our residual. Those are our errors. Does that make sense? That's how we can calculate that. Boop. And so now we can say heights with one more column. One more column called residual. And we can give back the residuals now. We can put into there the residuals of the table called heights with where we're using mid-parent to predict the child. And I can copy and paste that because that's a lot of type. Boop. And so that's my table, my new table. I'll just put that back into heights. Boop. And so in addition to the fitted values, now I have the residual values. It's like this was the prediction, this is the error. There's just synonyms now. So this is how far off it was. It was, all right, this one was, oh, did I do it in the wrong direction? No, this is actual minus estimate. So it's off by 2. This one should be increasing by 2 to get to the right value. This one should be decreasing by 1.5 to get to the correct value. That's our residuals, and we know how to calculate root mean squared error for those now. Root mean squared residual, I guess. And let us make some graphs now of these residual values. All right. So let's see here. Your book has some interesting functions here, and I guess I want to show them to you. Is it worth it to type them out? Probably not. Here, let me just steal more code. Dun, dun, dun. So these are some functions that are useful, and I'll show them to you. These are just some functions that generate some plots. So this is a function that generates a plot of all the fitted values. So it's like all of our estimates, all of our linear estimates next to the original values. This is plots that we've seen before, and this is a new one where we plot the residual value based on the x. So let me show both of these to you now for our mid-parent and child. Dun, dun, dun. So if I say plot fitted of our heights table, where we're using mid-parent to predict child, a lot of copying and pasting, don't mind me. What that looks like is this is the one we've seen already, right? Where we have our actual data and here are the fitted values. We can also graph the residuals. We can do both of them at the same time, plot residuals. It'll show us both. And let me explain what that one is doing. Same ideas. It's all right. Here are the, for all of the x values, we've got our predictions and we've got all our data points. Here's the residuals of all our predicted values. Do you see how it's just like an amorphous blob? Centered around 0, though. Like we'd like to have zero residual, 0 error for most of the values. And you see how they're like on both sides of that. Like we weren't too high or too low. We were just right in the middle. That's kind of telling you that okay, yeah, this was a linear thing that could be estimated with a line. It was a linear kind of correlated thing. There wasn't anything weird looking. This is the graph of the residuals for every x value, for every point in our graph. How far off was it? All of our residual values, these guys. So x values are the midparents and residual is the y values for this second graph here. Okay, that's what's going on, and they help you see nonlinearity. This is linear because there's no real trend to this. It's more like a blob centered around 0. But if it wasn't, then we're in trouble. So a residual plot should look like a blob for linear relations, but it will have patterns for nonlinear relations. And so let me prove that to you, and that will be one of the last things we do. So residual plots help you, I guess this is a subsection. Residual plots help you see nonlinearity. Boop. So here is a cute table about dugongs. It's so cute. All right, so table.read table. I didn't know that was an actual animal growing up. It's also the name of a Pokemon. Apparently, it's a real thing. Dugong. Boop. And so here's just a cute little table of a bunch of dugongs in the wild. And here's the length of them, I guess in meters most likely. And then how old they were in terms of age, with 0.5 ages too. Let's do a graph of age versus length. So length on the x, age on the y. It looks like the longer dugongs, they're of course older, they've grown more, but do you see how the trend is not a line, most likely? It's like it gets harder to get bigger, I guess, in the real world. It's strongly linearly correlated though. If you want to do a line, like we can ask for the correlation of the dugong table, or we're trying to use length to predict age. That's a thing. And it's decently strong. It's close to 1, but I think you can see, though, it's still not, it shouldn't really be a line. It's more of like a quadratic thing. And so we can plot that. We can plot fitted and plot residuals, just like we did here. Boop. But it's now these guys. Ta-da! So here is the best linear estimator. Here's the best fit line. And you see how it's kind of like cutting these off above, cutting these off below. It's trying to go in the middle of everything. Minimize root mean square error. That's what it's doing. But it shouldn't be a line predicting this stuff. And we can tell that from the residual graph. Do you see how it's, first of all, like here's 0. Everything should be kind of centered around 0. That's what it means. Like it wasn't too big or too small in terms of error, in terms of how far off it was. But do you see how there is no, this is not an amorphous blob anymore, like it was up here. Like this, you can't really read anything out of this residual plot. But this you can tell, like, okay, at the start, it was always a positive residual. In the middle, it was usually a negative residual. Towards the end, it got back to being a positive residual again. You see that? See how I can read that? that's telling you that, oh, this is probably not linear. It's not really working. It shouldn't, it's not centered around 0. The error is changing where it is. Whereas for a linear estimated thing, like the error shouldn't be changed. It should be all over the place, centered around 0. Does that kind of make sense? Because that meant it really was going between them all perfectly. This is not going between them all perfectly. It's trying to cut things off. All right. So that's telling you that, oh, this is probably not a linear thing. And yeah, I think that's most of what I wanted to say. We can do that for a couple more things, and that is most of what I wanted to tell you. Okay, yeah, let's see some more examples with our hybrid table. Where was that? Ta-da! Here's the hybrid table of all these cars, right? Did we change it to be select out only the SUVs? No. Let's just take the hybrid stuff only. So a bunch of cars again. Let's go back to these guys. We're a bunch of different vehicles with MSRPs, accelerations, and miles per gallon. Let's remember what we were trying to predict. We're doing like acceleration, MSRP, acceleration, and miles per gallon as well. So let's scroll back down and use the hybrid table now that I've re-included it. Whee! A lot of stuff in this chapter. Let's do, I don't know, these guys for acceleration, predicting miles per gallon. So hybrid, the acceleration, predicting miles per gallon. Because you would think that like a car that goes faster or can accelerate faster probably gets worse gas mileage. Ta-da! All right, so let's look at this graph and see if we see anything. So here's the best fit line. It looks like, yeah, as your acceleration goes, increases, the miles per gallon decreases, which I think makes sense in my mind. So it's a negatively correlated thing. And here's our best fit line trying to go between the data. This is the best line that minimizes root mean square error for all this data. And you can't really tell right now, like, oh, does that look linear? Does it not look linear? I don't think we looked at this graph before. I think this is one that we didn't see. But it looks like there's a lot of variation over here and not as much variation over here. I don't know if this is a line. Looking at the residual plot should hopefully tell us something. And what do we see? We see that it's probably a good linear estimate when the values aren't over here. Does that make sense? Here's a nice looking blob. This is, it's getting squished kind of over here. And that's something that's kind of not normal anymore, right? That's different. So maybe the higher values are better predicted by some other estimate. Like that's what it makes me think. So something like that. But amorphous blob, unassociated blob for linear relations. There will be patterns for nonlinear things. So it looks like towards the end here, values on the right look different than these values on the left. So something's happening to the graph. Something's happening that maybe is not linear. Okay? That's what it makes me think. So yeah, I hope that convinces you. But it could just be that there's some, yeah, this seems like it might be quadratic almost, like a decreasing curve. That might be a better line between all these. Maybe that's what the graph is saying. So just look at the residual plot. It doesn't like tell you what it is, oh, this was supposed to be quadratic or something. It just kind of gives you a hint to say that, oh, this maybe wasn't the best thing to use a linear predictor on. Yeah. Yeah, I think that's what I wanted to say. Any questions about that? These residual values for specifically linear regression do have some cool mathematical properties. Here's some facts. Let me show that to you. The average residual, we actually noticed this already, the average residual is 0. Like it wasn't, the whole fact that it was, because what it's doing is minimizing root mean squared error. It's trying to make sure that that is as small as possible. And so as many things as were above are now below. It's trying to like cut all your values in the middle as well as it can. That's why the mean of your errors, of your residuals, should be 0. So the average residuals is always 0. That's just what it means to do regression. That's what it means to have a good line between the data. That's the best fit. It's always going to cut things off as much up high as it does below, but where it does that is now the question. the average of residuals is always 0. Even if it's a nonlinear thing, it's going to try to draw the best line between them all, and that's going to cut it off. Average of residuals is always 0, so give me the residuals for the dugong, even the nonlinear thing, length versus age, or age versus length. Length on the x, predicting age, give me the mean of all those values. It's going to be 0. You have some Python float type errors, but this is a very small value, 8 point whatever times 10 to the negative 15. So it's 0. It really is 0. It's just off by some rounding factors. So usually you want to look at these like, take this value and round it. Take that value, round it to like 6 decimal places. It's 0, yeah. There's that. What else? Any of them. Even the hybrid one. No matter what you're trying to do, even if it's not linear, your residuals, their mean will be 0. It's trying to cut it off. Apparently negative 0 is possible in float land in Python. That is a little weird, admittedly, but that's okay. That's a thing. And then also, that means that, yeah, the root mean square error ends up being the standard deviation of your residuals. Does that make sense to us? Because the mean is 0. If you do the standard deviation, that means you're trying to subtract from the mean, and that means you're subtracting from 0. And so this formula kind of turns into, because subtracting from 0 does nothing, this turns into standard deviation calculation, technically. That's kind of cool to think about. That's what the root mean square error means, kind of. The values are, it's interesting that, let's see, the correlation with the x values, with the x values, I should say, that you're trying to predict from for residuals is always going to be 0. There's not going to be any pattern there. And same with the fitted values, which is weird to think about, but that's just what it means. It's trying to be unbiased. The correlation between the residuals and the predictor, you'll read more about this, are 0. So, like, for example, the correlation for the heights values, and then let's go back to here. We got our heights table, right? Here's the heights table. We got fitted values, we got residual values, and so let's ask for the correlation of that table where we're trying to use mid-parent to predict the residual values. How far off is it going to be? That's also going to be 0. It's like you can't tell anything from the residual value. You can't tell like, oh, because the value's up here, that means the residual is 2. It's trying to just like, as many as were above are now below. The error is, you can't predict where the error was going to be. That's all that means. That line is trying to go right between everybody. You can't say like, oh, over here, I know it's going to be a positive error. Over here, I know it's going to be a negative error. That's just, there's no correlation at all there. I hope that makes at least a little bit of sense. That is very confusing, I think. But that is just one of the facts that you can get out of what we're doing. But yeah, I think mean equals 0 should hopefully make a little bit of sense. Yeah. So that's what it means to have residuals and to look at their plots. I think what I mostly care about you is looking at the plot of them and noticing like, oh, this is not a blob. Something's wrong. Yeah, that's my idea. And I think that's most of what I wanted to say. That was a longer chapter. It took 3 lectures, but we got through it. We know now how to, at least for linear things or quadratic things, if you use the minimize function or some other function that you come up with similarly, we know how to take values that we've seen before and try to find where a new value might lie along a graph, where it might lie among values that we've seen before. You give me a new x, and I'll try to give you the y that it should be at, given y values for things close by, something like that. That's how we've predicted things. That's really cool. So we know how to do that now. Are there any questions about this chapter? Lots of code to go and look at and study for sure, but I think that's most of what I wanted to say. All right, so if we are good, we have a couple more assignments that depend on this chapter. You can imagine that there's a lot going on. There's 2 different assignments about it. So homework 10 and then lab 9. Let's do them in that order. So let's deal with due dates, and then I'll let you go off and work. Dun, dun, dun. Homework 10, lab 9. It looks like we got project 2 due in a week, so let's do Friday, the 14th, can be homework 10, and then the Wednesday, the 19th, can be lab 9. I think that's when I'll do it. Okay? So homework, so like we've got the 14th and then the 19th for the assignments. Okay? I think that'll be the order. And I think that's all that I want to say. Any last questions to have on the recording before we stop? All right, friends, we did